chemistry. So our first lesson in this Unit 7, dealt with net ionic equations, dealing with ionic bonds. Now we're going to cover the subject of how covalent bonds are created. So drawing Lewis dot structures for molecules, that's going to be the main point in this lesson. So there are two goals when creating a covalent bond. One, all valence electrons contributed by the bonded atoms must be placed in the molecule. So remember, the valence electrons are the ones on the outside orbital, and those are the only ones shown in Lewis dot structures, and we're going to be using Lewis dot structures to do this. And two, all atoms must have full octets. There's limited exceptions, and we'll discuss those at the end of this lesson. So one, these are the rules. I'm going to go through them quickly because they won't make any sense until you see examples. So let me just read through these quickly. So number one, determine the total number of valence electrons in all of the atoms that are going to be part of the molecule. Two, draw the structure. A, the least electronegative atom occupies the center of the molecule and is usually written first in the formula. B, hydrogen and fluorine must occupy outside, which are called terminal positions. Those are the outside atoms in the molecule. And we'll talk about why those two particular elements have to be terminal. 3, connect the outside atoms with the central atom using single bonds. 4, create octets around all terminal outside atoms. 5, assign remaining electrons as lone pairs around the central atom. 6, form multiple bonds, in other words, double or triple bonds, with the central atom if necessary. And those are the rules. Okay, so let's just get to it and with some examples. So example, H2O, we're going to draw that. You've seen that already drawn in this class many times. So number one, determine the total number of valence electrons. So we have two hydrogen atoms. Each one has one electron. Remember, E minus is the symbol for an electron. And then you have an oxygen, and it has 6 valence electrons. These are valence electrons. So the oxygen's valence electrons are in the second orbital. Hydrogen's valence electron is in the first orbital. So when we add those up, we have a total of 8 valence electrons to work with. So we have to place those to complete the Lewis dot structure. So a water molecule has a total of 8 valence electrons. Step 2, draw the structure. So A, the least electronegative atom occupies the center of the molecule and is usually written first in the formula. Hydrogen and fluorine must occupy outside terminal positions. So there we go. So you have these two in conflict. Hydrogen is less electronegative than oxygen. So rule A says that hydrogen should be in the middle. But rule B says that hydrogen must be an outside in a terminal position. So why is that? So rules 2A and 2B conflict. Hydrogen is less electronegative than oxygen. However, hydrogen can bond in only one location. So hydrogen cannot be a central atom, therefore oxygen is placed as the central atom. So again, think about that. Hydrogen only has one electron. It can only bond on one side. It can't be a central atom if it can only bond on one side. A central atom has to be able to bond in at least 2 different locations so that it can be in the center of at least two additional atoms. So hydrogen can't do that. So hydrogen is going to be the terminal atom in water. It always has to be a terminal atom. Okay, connect the outside atoms with the central atom using single bonds. So there we did that. We connected the oxygen with the hydrogen on the left and with the hydrogen on the right. So now we've used 4 out of the 8 electrons. Step 4, create octets for all terminal atoms. While hydrogen can only have 2 electrons in its octet, it has a full octet when it has 2 electrons. Remember, only hydrogen and helium in the first row have full octets when they have 2 electrons. Everything else on the periodic table requires 8 electrons to have a full octet. Therefore, we can't add any more electrons to hydrogen. 2 is the maximum that it can hold. So each hydrogen already has a full valence orbital with 2 electrons. Assign remaining electrons as lone pairs around the central atom. So we can go ahead and do that. And there we did that. We added 2 lone pair on the top, 2 lone pair on the bottom. For multiple bonds with the central atom if necessary. In this case, it's not necessary. So let's look at this. We've used all 8 electrons that we had to start with, and we've created an octet with all of the atoms. Oxygen has 8, and each hydrogen has 2, which is a full octet for hydrogen. So we've satisfied both of the rules. We've used all of the valence electrons, and we've created octets for all of the elements. So the 2 requirements of a covalent bond have been met. 1, all valence electrons have been placed. We started off with 8, and you can see that there's 8 there. And 2, all atoms have full octets. Two other notes about the Lewis structure for water. The bonding electron pairs can be represented by a line as shown on the right. So you see that line over there between the oxygen and each of the hydrogens. That one line represents 2 electrons. So non-bonding lone pair electrons cannot be shown in this way. In fact, usually when you use this stick figure structure over on the right, you don't show the lone pairs. You would just show the bonding pairs, not the lone pairs, but in this case I showed both. 2, the water is not a linear straight molecule as shown below. The rules for determining the geometry of a molecule will be covered later. They're covered in AP. I don't think I'm going to get to them in these classes. Maybe we will. We'll see if we can squeeze it in. Okay, now we're going to create the Lewis dot for oxygen, O2, because oxygen is one of the 7 diatomic molecules. In nature, it appears as an O2 molecule, not as individual oxygen atoms. The oxygen that you breathe in every time you take a breath is O2 molecules. So 1, determine the total number of valence electrons. So we have 2 atoms of oxygen, each have 6 valence electrons. Be sure you know how to determine that. It's the 6th element from the left in the 2nd row. That means it has 6 valence electrons. So the 2 of them together have a total of 12 valence electrons. So an oxygen molecule has a total of 12 valence electrons. Draw the structure. The least electronegative atom occupies the center of the molecule and is usually written first in the formula. Hydrogen and fluorine must occupy outside terminal positions. Well, you only have 2 atoms, oxygen, so there's only one configuration. It's an O next to an O. Okay, that's pretty basic. Okay, both oxygen atoms are considered to be central atoms. 3, connect the outside atoms with the central atom using single bonds. So there we've connected the 2 oxygen atoms with a single bond. So we've used 2 out of the 12 valence electrons. Create octets for all terminal outside atoms. So they're also both considered to be terminal atoms since they're both on the outside. So we're going to go ahead and put octets around both of them. So you can see both oxygens now have an octet. They share those 2 central electrons, so those count for both of the oxygen atoms. So they both have 8. Now, if you count how many total electrons there, you have 14. That's too many. We only had 12 to start with. We can only end up with 12. So reduce the number of electrons to the number computed in step 1 by eliminating lone pair electrons. Assign remaining electrons as lone pairs around the central atom. Well, you can pick any lone pair you want. We're going to pick the one on the right side there, and we can choose which lone pair to remove. We're going to remove that one, and there it goes. So now we have the correct number of electrons. We have 12 valence electrons. That's how many we started with. Okay. The problem now, though, is that the oxygen on the right does not have an octet. So form multiple bonds with the central atom if necessary. So this is where step 6 comes in. It is necessary. So think about how you can rearrange those. You don't want to add or subtract electrons. We have the correct number. It's 12. But how can you rearrange them so that both oxygens have an octet? Think about it. Okay, here it is. You take a lone pair from the outside. It doesn't matter which lone pair. I happen to take the one on the left, and you move it in between. So now you've created a double bond. So if you now look, we've used 12 electrons. That's what we needed to use, and both oxygens have an octet. They have 8 electrons because those 4 central electrons count for both of the oxygens. So we have met both requirements for a covalent bond. We used all 12 of the valence electrons, and we created octets around both oxygen atoms. Now we're going to do hydrocyanide, and we're going to determine the total number of valence electrons. So hydrogen has 1, carbon has 4, and nitrogen has 5. Again, find that on your periodic table. Be sure you know how to get those numbers. So there's a total of 10 valence electrons that we need to account for. An HCN molecule has a total of 10 valence electrons, which must be placed in the molecule. Draw the structure. So the least electronegative atom occupies the center of the molecule and is usually written first in the formula. Hydrogen and fluorine must occupy outside terminal positions. So the electronegativities from the periodic table of electronegativities that's in your reference sheets. Hydrogen has an electronegativity of 2.1, carbon has an electronegativity of 2.5, and nitrogen has an electronegativity of 3.0. So we can see that hydrogen is the least electronegative, but again, as we saw in the previous example, hydrogen cannot be a central atom. It only can bond on one side, so it cannot be in between bonding with 2 different atoms. Therefore, carbon is going to be the least electronegative atom that can bond on more than one side. So we're going to put carbon in the middle. So hydrogen has the lowest electronegativity, but it cannot be a central atom. This makes carbon the central atom. So the structure for the molecule is HCN. So connect the outside atoms with the central atom using single bonds. Okay, so there we go. We just did that. So we've used 4 of the 10 electrons that we have to account for. Create octets for all terminal outside atoms. So hydrogen already has a full octet because it has 2 electrons and that's all it can hold in its first orbital. But we can put an octet around nitrogen. So now nitrogen has an octet, hydrogen has an octet, carbon does not have an octet. So we've used 10 electrons, that's the number that we have to work with, but carbon doesn't have an octet. So we need to do something about that without adding or subtracting electrons. So how do we do that? Think about it. Think about the last example. We have now used the 10 valence electrons. However, carbon does not have an octet. Rearrange the lone pair electrons to create an octet for carbon. So here we go. And that's how you do that. Okay, so we moved 2 of the lone pairs that were around nitrogen, moved them in between carbon and nitrogen. Now all of the atoms have an octet, and we've used the 10 electrons. So we create a triple bond between carbon and nitrogen. This fulfills the 2 requirements for a covalent bond. We have used all 10 valence electrons, and we have created octets for all elements. The 6 electrons in the triple bond are counted for both carbon and nitrogen. Those 6 in between the C and the N count for both of those atoms. Now there are some exceptions to the octet rule, so we'll just cover those here. There's not a lot of them, but elements in group 13, if you look at the column that has boron, B, are exceptions to the octet rule. That would be boron and aluminum, for example. So elements in group 13 compounds have only 6 valence electrons. So if you wanted to make boron trihydride, it would look like that. So the boron has 6 valence electrons around it, and that's how you would create that compound. Aluminum right below boron would be similar. If you wanted to create a compound of aluminum and chloride, then you would have 3 chlorides around, not 4. Okay. All right, so those are the 2 exceptions that are really notable to the octet rule. And that takes care of this lesson on covalent bonds and how to create them.